to a new problem solving session. I tried something colorful, though I don't know the colors, but I think it turned out pink and it's a nice color. So we have something at the screen for you, and here is the problem. If you can see it, a flat, a flat shape consisting of three squares of side A. You can see here, everything is a square and having a side length A made of same wire. A small size capacitor of the capacitance C soldered into a wire segment. The whole system is placed in a uniform magnetic field, you can see here, perpendicular to the shape plane, that means in this direction. Symbol is already provided, the direction of magnetic field, and the magnetic field slowly increases at a constant rate K. So dV by dt is K, and K is of course positive. The resistance of the wire segment of the length A is equal to R. You can see here, each wire segment has a resistance R. Determine for the steady state, that means we have to solve this problem in the steady state, and that means something is going to happen. We will analyze it pretty soon. A magnitude and direction of the current in the segment AB. We need to find out current flowing in the steady state. Charge Q is stored by the capacitor, and the signs of plate charges, that means we have to, which plane is positive and which plane is negative, we have to find it out, and amount of heat generated in the circuit in time t, time tau, power, and then we will find the time. But how are we going to analyze this problem? This is the main thing. The magnetic field is like this, in this direction, and it's increasing. So there are loops, and they are going to oppose this increase in magnetic flux through them, and then they will produce a magnetic field in this direction opposite to the increasing magnetic field. That means they are going to produce EMF that will drive the current in the circuit in clockwise direction. So direction of current is, well, I think this loop, and in this loop the current will flow like this, and this loop current is going to flow like this. I'm thinking loop wise, so it will keep doing like this. Well, so as far as this loop is concerned, I don't know. In this loop, in this wire, the current direction will be obviously downward, no problem at all. And in this loop, in this wire too, when it means in this wire AB, the current is going to flow in this direction, and that is not a problem. But in this wire, a current will be flowing like this, and this current will flow like this. So I don't know the direction, so I just assume that this current will be in this direction. Just assumed it, I don't know, because in this wire current may flow in a direction opposite to the direction shown in the figure. I don't know. So when we don't know something, we just assume a direction, a particular direction. I'm going to name it as well. name it this current as I1, and this current will be I2 or I3 because this is confusing, and I will name this current as I2. So, and there will be no current flowing through this wire, that is I should name it, this is A, this is B, then this is C, this point is D, this point is E, this point is F, this point is G, and this point in H, this point as H. Then in the wire HC or CH, there is no current, there will be no current in the steady state, because we all know that the famous capacitor formula, C equals Q by V, so Q equals C V, and if we differentiate it, this is not going to change, and so we can differentiate and write things like this. And when capacitor goes into the steady state, we know that the voltage across it neither gets charged or not discharged. That means no charging or discharging takes place. In that case, potential difference across the capacitor should remain constant, and that means dc by dt will become 0, so no current will pass through the capacitor in a steady state. I will remember this picture. So EMFs will be all produced in all the loops as a consequence of electromagnetic induction, because flux is changing in each and every loop. And what will be their values and how are we going to proceed it? We just made an elementary plan, and now we are going to execute this, but I need to remove this picture and draw it again. So I got what? Here is a wire and a capacitor here. There were 3 loops like this, and all are square, and each wire has resistance R, a small r. As you can remember, it was given in the problem. And the name of this point was A, B, C, D, E, F, G and H, and the current is going to flow in this wire AB. I assumed it I1. Its value, I just assumed that its value may be I1 and its direction is correct. And in this wire FE, the current will flow in this direction, and I named it I2. In the wire GD, the current may flow in any direction, either downward or upward, but I have deliberately taken it downwards, and let's name it I3. We don't know any of the values, either of I1 or I2 or I3. We don't know any of the values, but we can find. Think about this loop. Magnetic field is increasing at a constant rate. That was given that dV by dt was K. So the induced EMF in this loop will be, I know the induced EMF we write in such cases as rate of change of flux, that ultimately turns out simply like dV by dt multiplied by area. So if I consider the whole loop, that means if I consider the loop, just to name it A, F, EB, the whole loop. Then the area will be 3A square, and the magnetic field is B everywhere. So, and it keeps increasing at the rate K. So I can write here Ka, and its value is going to be K 3A square, because every square has an area A square, because side length of the square is A. So the every loop has an area A square, and in this entire loop the area is 3A square. And if I take loop number 2, that is AG dB, the rate of change of magnetic field, rate of increase of magnetic field is a constant, that is equal to K, and area is simply 2A square. So why did I consider these two loops? I'm going to explain you pretty soon. But one more thing, since no current passes through it, if I wish I can remove it for a moment, this loop, this wire, because no current is passing through it. So current is passing in this loop and this. I'm going to apply the loop law, Kirchhoff's loop law, and it's because it's elementary and very simple, so I am willing to apply it. But first, let me write something else. You can see here I1 is incoming current at this junction, and I2 just passing from it, and I3 also. So can I write the Kirchhoff's first law first at junction at the node G? And I'm going to do one thing. I'm going to write Kirchhoff's first law, current law, KCL you call it. I simply called Kirchhoff's first law at node G. You can call it a node or a junction, whatever you wish. And I can see here that I1 is equal to I2 plus I3. And then I'm going to use the Kirchhoff's loop law, that is Kirchhoff's second law, for these two loops. Because I have the EMFs for them, so if I'm willing to write the Kirchhoff's loop law for these two loops, there is nothing wrong in it. And Kirchhoff's second law for loops AFEB and AGDB. So what can I write for Kirchhoff's second law for loop AFEB first? What can I write? The EMF is equal to the net current. Net EMF equals net voltage provided to the circuit. Net EMF in the circuit equals net IR terms, voltages they are consuming. So the net EMF in this loop is K3A square, and what voltages they are consuming. So you can see this I1 passes everyone can see it. Yes. So I1 passes from and for I1, I2 passes in this loop and I1 is this loop's current, and I1 faces a resistance 1, 2, 3, 4, 5, 5R. So I can write it here, I1 multiplied by 5R, I1 multiplied by 5R for the left loop, and I2 multiplied by 3R for the right loop. You can see here 3 wires and all having resistance R, so they are consuming so much of voltage, I2 multiplied by 3R, and this loop is consuming, and for both loops the EMF provided is 3K square and they are consuming this much voltage. So this is the Kirchhoff's second law for the bigger loop, which is AFEB. And now I can do one thing, I can write the Kirchhoff's second law for this loop, that is AHBD. And for AHBD, the EMF is K multiplied by 2A square, that is 2Ka square is the EMF provided through that loop, and voltages they are consuming is again I1 multiplied by 5R from here to here, and this I3 is using only resistance R, so it is consuming only I3 multiplied by R. So we have these three equations and we have to solve the whole system based on it. What can I do now? K square upon R. Continuously, we have three equations, right? Three equations. And these three equations can be used to solve this problem. I1, to find out I1, I2 and I3. So we have three unknowns and three equations. Everything else is given. K is given, A is given. So what do you need to find and what are given? It should be your priority when solving a problem. And for the sake of simplicity, if I put K square upon R as I naught, this I naught is known because K is known, A square is known, and a small r is known. So if I put here, I can get the results like 3K square upon R, that is 3 I naught equals 5 I1 plus 3 I2, of course, and here K square upon R is 2 I naught and it will be 5 I1 plus I3 only. But we haven't used this equation, that is I1 equals I2 plus I3, and if I put I1 equals I2 plus I3, I1 equals I1 plus I3, so I can write this set of equation as 3 I naught equals 5 I2 plus 3 I2, that is 8 I2 plus 5 I3. I just placed I1 equals I2 plus I3 in these equations, and 2I naught will be 5I2, of course 5I2 plus 6I3, and I know now you can find I2 and I3 easily. Even if you are a class 10 students, you have a set of equations, two unknowns. I1 is known, and perhaps I have got the values earlier when I solved it. I got the values of I1. I may be incorrect, so kindly check it. I1 equals 9 upon 23 I naught, and I2 equals 8 upon 23 I naught. And what was the value of I3? That was I naught upon 23. So I already got the values I1, I2 and I3. So this current was required, and I know I naught is already provided, that is Ka square upon R. So here, so the first part of the problem has been solved. Now we need to solve the second part, the charge on the capacitor, and which part is positive, which one is positive and which one is negative plate. So I bring the capacitor back here, and I know from here or here I can take either of the loops. This capacitor is driven by the voltage Ka square. This capacitor is driven by the voltage Ka square. Should I remove all those things? Because the problem has been solved and we don't need these items. So I'm going to rub them out, and you can see this capacitor is being driven by the voltage K. Oh, what is this? Oh, Ka square, here or here. But I will take this loop, this contour AHBC, and the voltage provided to the capacitor is Ka square. And I can write something else. This Ka square is equal to the current. This Ka square is being used by this current I1. If I consider this loop, this Ka square being used by these three wires. So I can write the K square being used by I1 in this loop through three resistances. So sorry, this current is I1 and this voltage is being used by this I1 through these three wires and the capacitor itself. So this is voltage VC, voltage consumed by capacitor, and we have the value of I1 already. And what was the value of I1? I have already found it, 9 by 23 I naught. So I can write few things here, that K square equals 9 upon 23. I1 is 9 upon 23 I naught, that is K A square upon R multiplied by 3R plus Vc. So if I cancel this R, I will get K square equals 9 multiplied by 3 is 27 Ka square upon 23 plus Vc, and this is what Vc is equal to 1 minus 27 upon 23 Ka square, and that means we got Vc equals minus 4 Ka square upon 23 minus 4 upon 23 Ka square. This should be given some respect. The voltage is minus 4 upon 23 K square. The voltage across capacitor, and I have written like Vc, that means this Vc is basically Vh minus Vc, and it's negative, that means this end is negative and this end is positive. The upper end is negative and lower end is positive, because Vh minus Vc is negative, that means Vh is less than Vc, and it can be in only way when Vh is negative and Vc is positive. So I have found the polarities as well. Now I need to find out the total heat developed in the circuit in time tau. So to find out, I can only think that these resistances are, so capacitor is gone, capacitor is storing something, capacitor is not participating in this game, in this energy game, energy dissipating game. It's a very gentle device that stores the energy, that means this I1 is dissipating power, and how much power is it dissipating? Let me remove all those things. So I'll have the figure and the space both by my side. So you should be here, you are right here. And I1 is dissipating power, I1 square multiplied by 5R, I square R, and this I2 is also dissipating power like I2 square multiplied by 3R, and this I3 is dissipating, I don't know, less or more, because I forgot the value of I3 and I2. I1 I can still remember, it was 9 upon 23 I naught, and there was something I2 and I3, I don't know how much in time t. So this is the power, so in time t we need to multiply all of them by time tau, and this will be the whole power. H was not, H is also taken here, it was written perhaps W. So in time tau, the total power, the total heat lost by the circuit is this. You can put the values of I1, I2 and I3 and get your result. I don't have the result, but because I didn't calculate it, sorry. And thank you very much for watching as well.